A comet is doing something it shouldn't, and scientists are struggling to explain it. 3I/Atlas, a visitor from another star, has crossed into our solar system, but its behavior is defying everything we know about comets. Its tail is pointing straight at the sun, its glow has turned an eerie green, and it's brightening far faster than anyone predicted. What could be happening here? Why is this comet acting so differently? And what happens when this cosmic enigma gets closer to our sun? Stay tuned as we uncover the mysteries of 3I/Atlas, an interstellar visitor that's about to rewrite everything we thought we knew about comets and space. The skies above us have always been a realm of wonder. Yet, even in the vast expanse of space, unexpected visitors from other star systems rarely make themselves known. But when they do, the stories they tell are nothing short of extraordinary. Enter 3I/Atlas, a comet unlike anything we've ever seen before. This is no ordinary object traveling through our solar system. It is an interstellar wanderer, a relic from another star, carrying secrets no human has ever glimpsed. 3I/Atlas was first spotted in July 2025, as it appeared as little more than a faint streak of light against the starry backdrop. At first, astronomers thought it might just be another comet, following the same predictable patterns as countless others before it. But as the days passed, something remarkable happened. The comet began to brighten at an alarming rate, far faster than any model predicted. By mid-September, it had surged in brightness, surprising scientists who had anticipated a much more gradual change. But what was driving this sudden acceleration? And that was just the beginning. As 3I/Atlas continued its approach toward the inner solar system, astronomers began to notice something even more bizarre. Its tail, traditionally a feature that streams away from the sun, was pointing directly at it, an impossibility according to the laws of cometary physics. But there it was, defying everything we know about how comets should behave. And if that wasn't strange enough, the comet's glow shifted, taking on a vivid, eerie green hue, something never before seen in an interstellar object. In the world of astronomy, comets are usually predictable, their behavior shaped by the simple, timeless physics of our solar system. Yet, 3I/Atlas seems to disregard these rules entirely, creating a whirlwind of questions that no one can easily answer. Why is it doing this? What forces are at play? Is this comet just an anomaly, or is it telling us something more profound about the universe beyond our stars? As 3I/Atlas hurtles toward its closest approach to the sun, the stakes couldn't be higher. The closer it gets, the more bizarre and unpredictable its behavior becomes. Could this be the moment when it reveals its true nature, or will it fade back into the darkness, leaving scientists with more questions than answers? Whatever happens next, one thing is certain: this comet is rewriting the rulebook on space science, and the mysteries it holds may change everything we thought we knew about comets, interstellar visitors, and the very nature of the cosmos itself. The universe is filled with countless mysteries, but some objects in space seem to possess the uncanny ability to defy all expectations. 3I/Atlas is one such object. The comet's sudden and unexplained brightness surge in mid-September 2025 marked the first sign that it was no ordinary traveler. What should have been a slow and predictable increase in luminosity as it passed closer to the sun turned into an extraordinary acceleration that left astronomers scrambling for answers. To understand the significance of this brightening, we need to first grasp the concept of astronomical magnitudes. Magnitudes measure the brightness of celestial objects, but in an inverted scale, the lower the number, the brighter the object. For example, the sun has an apparent magnitude of -26.7, while the dimmest objects visible to the naked eye on a clear night hover around a magnitude of 6. So, a comet with a magnitude of 15 or 16, typically faint and barely detectable, would become increasingly visible as it brightened. However, when 3I/Atlas first crossed into our solar system, astronomers expected it to reach a magnitude of around 15 or 16 at its closest approach, which was consistent with the behavior of other comets in its category. But that prediction quickly proved false. By mid-September, the comet's magnitude had dropped to a startling 12 to 14. For those unfamiliar with magnitude shifts, this change is drastic. A decrease of just 2 magnitudes means the comet is emitting 6 times more light than originally predicted, a dramatic and surprising increase in brightness. To put this in perspective, consider that a comet typically brightens as it nears the sun. The heat causes volatile materials, like water and carbon dioxide, to vaporize, forming the coma, a cloud of gas and dust, and the tail. This outgassing process should be gradual, following a predictable pattern as the comet approaches perihelion, the closest point to the sun. But 3I/Atlas wasn't following any model. Its brightness surge was not just unexpected, it was unprecedented. The question immediately posed itself: why was 3I/Atlas brightening so much faster than anticipated? Scientists began to explore potential causes. One of the most plausible explanations lies in the nature of the comet's outgassing. As 3I/Atlas approached the sun, the increase in solar radiation would have heated up the icy core of the comet, causing volatile ices, like water and carbon dioxide, to sublimate. This means they would transition directly from solid to gas, carrying dust and debris away from the nucleus, creating the bright coma that surrounds a comet. In most comets, this outgassing process is gradual, with the most volatile substances being released first as the sun's heat intensifies. However, with 3I/Atlas, something extraordinary was happening. The speed at which its brightness was accelerating suggested that volatile ices were sublimating at an extreme rate, far faster than what was expected for a comet of its type. This rapid outgassing could explain the dramatic brightness increase, but it raised another alarming possibility: instability. In the cometary world, rapid brightening often signals a potential breakdown. As volatile compounds sublimate, the internal structure of the comet can become unstable. Comets aren't solid bodies like asteroids, they're more like loosely held together ice and rock piles. If a comet expels material too quickly, it can fracture, breaking into multiple pieces or disintegrating entirely. Fragmentation events like these are rare, but not unheard of, especially when the comet is experiencing unusually high outgassing. This idea of instability became even more concerning when scientists began to speculate about the composition of 3I/Atlas. If the comet was composed of exotic ices, materials that had never before been exposed to the intense solar radiation of our system, could it be more volatile than we thought? Some researchers even began to consider the possibility that 3I/Atlas wasn't just behaving like a typical comet, but might be experiencing an outgassing event so violent it could lead to its rapid depletion of volatile materials, something that could cause it to fade just as quickly as it brightened. And yet, this wasn't the only possibility. The behavior of 3I/Atlas might indicate that it contains some unknown compound, or that it's formed from materials in a way that we've never seen before. There is a profound mystery in its brightness surge, one that can't be explained purely by the outgassing of carbon dioxide or water vapor. Could there be other, more exotic compounds at play? Could the comet's very composition hold secrets to the nature of star systems far from our own, preserved in its icy core for millions, if not billions, of years? As scientists observed the comet's rapidly increasing brightness, they were not only watching an extraordinary event unfold in real time, they were witnessing the unmasking of a cosmic riddle. Was this just a comet, or was 3I/Atlas offering something far more profound, something that could change everything we think we know about comets, interstellar objects, and the physics that govern them? The idea of visitors from distant stars is one that has fascinated humanity for centuries. Yet, most of the time, these celestial travelers are little more than a distant dream. That is, until 3I/Atlas arrived. Unlike anything we've encountered before, this comet is not native to our solar system. It hails from far beyond our neighborhood in space, an interstellar traveler carrying with it the secrets of another star system. In the world of astronomy, objects like 3I/Atlas are incredibly rare. Its designation, 3I, tells us all we need to know about its origins. The I stands for interstellar, and the number 3 means it is only the third confirmed interstellar object to ever be observed passing through our solar system. The first, Oumuamua, in 2017, left us perplexed with its strange shape and non-gravitational acceleration. The second, Borisov, arrived in 2019, behaving more like a typical comet but revealing strange chemical compositions. Now, 3I/Atlas enters the scene with a story that may eclipse both. This comet is much more than just a visitor from another star. It is a time capsule, an ancient relic of a distant star system, traveling across vast stretches of interstellar space to finally make its way into our solar system. The materials that formed this comet were never exposed to the heat of our sun, the same as other objects in our cosmic neighborhood. They've existed in the cold vacuum of space, preserved in their primordial form, untouched by the forces that shaped our own solar system. For astronomers, the implications are profound. 3I/Atlas represents a snapshot of the conditions that existed around another star, potentially millions or even billions of years ago. Could this object carry clues about how planets, moons, and other celestial bodies formed in a different star system? Perhaps the chemical building blocks of life, preserved in pristine condition, were formed under conditions vastly different from our own sun's influence. But what, exactly, is inside this time capsule? Scientists speculate that 3I/Atlas may contain ancient ices, perhaps even elements of the same chemical soup that gave rise to our own solar system. This could be our first glimpse into the building blocks of another solar system. What if, within its icy depths, lie compounds or molecules that we've never seen before? Could there be alien chemistry within this object, so foreign to us that it challenges our current understanding of molecular biology and planetary science? The excitement among the scientific community is palpable. Never before have we had such an opportunity to study an object that predates our own sun, one that has traveled across the galaxy without ever encountering our star's unique radiation environment. But with this excitement comes a great deal of uncertainty. The comet's behavior is unlike anything seen before, its strange green glow, its tail pointing toward the sun, and the rapid brightening all suggest that 3I/Atlas may not just be a simple comet but a relic that could rewrite the rules of cometary science. As astronomers continue to observe 3I/Atlas, the sense of awe is mixed with a feeling of trepidation. The comet is not just a scientific anomaly, it is an interstellar ambassador that may reveal answers to questions we didn't even know to ask. Its chemical composition, the very structure of its nucleus, may provide insights into how other star systems evolve and what lies beyond the familiar environment of our sun. The possibility that 3I/Atlas could hold alien chemistry, materials and compounds formed under conditions that differ drastically from anything we've encountered before, has sent waves of anticipation through the global scientific community. But there is also a growing sense of humility. We are peering into the unknown, trying to unlock the secrets of a distant past that may hold answers to questions about the very origins of life, planets, and the cosmos itself. Yet, even with the best tools at their disposal, scientists are confronted with the reality that much of the comet's true nature remains hidden. It's a cosmic enigma, and no one yet knows what exactly we'll find when we finally crack open this interstellar time capsule. Could it be the discovery of a lifetime? Or will it challenge the very fabric of what we know about space, time, and the building blocks of life? As 3I/Atlas draws closer to the sun, the questions continue to mount. Will it offer us answers, or will it leave us with even more mysteries? Whatever the outcome, one thing is certain: this interstellar visitor is forever altering the way we look at the universe. As 3I/Atlas hurtles toward the sun, the cosmic clock is ticking. For astronomers, every day brings us closer to a series of critical events that will determine how much we can learn from this extraordinary visitor. The comet's path through the solar system has been mapped with precision, and two key dates stand out on the timeline: the close approach to Mars on October 3, 2025, and perihelion, its closest point to the sun, on October 29 to 30, 2025. October 3rd will mark the comet's closest encounter with Mars, a mere 30 million kilometers away. In cosmic terms, this is an incredibly close approach. For reference, Earth is about 150 million kilometers from the Sun, so this proximity to Mars places 3I/Atlas well within the range of several spacecraft currently orbiting the red planet. This alignment of timing and geometry presents a unique opportunity to study the comet in unprecedented detail. Mars orbiters will be in an optimal position to capture data that may otherwise remain hidden from Earth-based observers. But these critical observations may not last long. As October progresses, the Sun's overwhelming glare will increasingly obscure 3I/Atlas from view, making Earth-based observations virtually impossible. This brings us to perihelion, which will occur between October 29th and 30th, 2025, when 3I/Atlas makes its closest approach to the Sun, reaching a distance of just 1.36 to 1.4 astronomical units. In simpler terms, this is slightly closer than the distance between Mars and the Sun. During perihelion, the comet will experience solar heating at its most intense. This is when it will likely undergo the most dramatic transformations, potentially leading to a massive outburst of gases and dust, revealing much more about its chemical makeup and internal structure. However, this period of maximum activity also coincides with one of the most challenging observational windows for Earth-based telescopes. As 3I/Atlas approaches perihelion, it will enter what astronomers call superior conjunction, a phase when the comet will be positioned too close to the Sun in the sky to be observed from Earth. The Sun's bright glare will drown out any light from the comet, making it nearly invisible to our telescopes. The Sun's intense radiation will also cause the comet to heat up rapidly, potentially triggering explosive outgassing events. However, these dramatic changes may unfold largely out of view, hidden by the blinding solar light. This presents a significant problem for scientists, who will be forced to rely on spacecraft positioned further out in the solar system to continue observing the comet during this critical time. While Earth is effectively blinded during perihelion, the role of Mars orbiters becomes crucial. Mars, located just under half the distance between Earth and the Sun, will provide a perfect vantage point. Spacecraft like the European Space Agency's Mars Express and NASA's Mars Reconnaissance Orbiter will be in the ideal position to study 3I/Atlas as it passes by the red planet. These Mars-based spacecraft are designed to observe planetary atmospheres, surface features, and other phenomena. Now, they will be called upon to become humanity's eyes on 3I/Atlas, studying the comet during its most active and unpredictable period. Mars orbiters will use their specialized instruments to gather data about the comet's coma, tail, and nucleus, areas that Earth-based telescopes will not be able to scrutinize due to the solar glare. The Mars Express orbiter, with its high-resolution imaging system, may provide some of the clearest photographs of 3I/Atlas yet. Meanwhile, NASA's MAVEN, Mars Atmosphere and Volatile Evolution mission, could offer vital spectroscopic data, shedding light on the comet's chemical composition. These spacecraft will be able to monitor the changes in the comet's behavior as it is bathed in the Sun's radiation, tracking shifts in its outgassing and observing any potential fragmentation or dust clouds it might eject. The close approach to Mars is not just a scientific opportunity, it's a race against time. As the comet draws nearer to the Sun, its rapid acceleration will continue, and the pressure will mount for scientists to capture as much data as possible before it becomes hidden from Earth-based instruments. The importance of Mars-based spacecraft cannot be overstated. Their ability to observe 3I/Atlas during this critical period will be invaluable for understanding the comet's transformation and gaining insights into the dynamics of interstellar objects. For a brief window of time, these spacecraft will be the only ones able to monitor the comet up close, offering clues to its mysterious behavior and revealing what makes this interstellar visitor so unique. While Earth-based telescopes will be left in the dark, the spacecraft orbiting Mars will hold the key to unlocking the secrets of 3I/Atlas during its most dramatic phase. The strange behaviors of 3I/Atlas have defied every rule in the cometary playbook, leaving astronomers stunned and puzzled at every turn. Its tail, typically the most iconic feature of any comet, is doing the unthinkable. It's pointing toward the sun. This isn't just a subtle anomaly, it's a complete violation of the laws that govern how comets should behave. To understand why this is so extraordinary, we first need to explore a phenomenon that is turning heads in the scientific community, the anti-tail. In the conventional understanding of comet physics, a comet's tail is formed when solar radiation heats the comet's nucleus, causing volatile ices to sublimate and release gas and dust into space. As the gas and dust are pushed away from the sun by the pressure of solar radiation, they form the tail, which stretches out in the opposite direction. This tail always points away from the sun, a predictable result of the forces at play. But 3I/Atlas is doing something altogether different. Its tail, its anti-tail, points directly toward the sun. This completely contradicts what we know about comet behavior, and it's sparking a fierce debate among scientists. An anti-tail is a rare and unexpected phenomenon in the world of comets, and its presence in 3I/Atlas has left many scratching their heads. Traditionally, anti-tails are thought to form due to specific conditions involving dust and gas particles being illuminated in a way that causes them to appear to move in the opposite direction of the comet's usual tail. But the anti-tail of 3I/Atlas isn't just a fleeting illusion, it's a stable, sustained feature that's visible over extended periods, raising the question, what's making it so persistent? The most likely explanation for this extraordinary behavior involves the size and composition of the dust grains in the comet's tail. Unlike typical cometary dust, which is small and easily pushed away from the sun by radiation pressure, the dust around 3I/Atlas appears to be much larger. Larger dust grains, heavier and more resistant to solar radiation pressure, can maintain their trajectories in the direction of the sun, resulting in the anti-tail. This theory is supported by recent observations showing that the comet's dust particles have unusual size distributions compared to other comets in our solar system. But even this explanation doesn't fully account for the persistent nature of the anti-tail. Some researchers have suggested that plasma dynamics, the interactions between charged particles in the comet's coma and the solar wind, could be playing a role. The solar wind, a constant stream of charged particles emitted by the sun, can ionize the gases surrounding a comet, creating a plasma tail. This plasma is influenced by magnetic fields and electromagnetic forces, which could cause the material to behave in ways that defy the typical cometary tail model. The interaction between the comet's outgassing and the solar wind may be funneling material in the direction of the sun, creating the anti-tail that is so perplexing. But the anti-tail is not the only unusual phenomenon surrounding 3I/Atlas. The coma, the fuzzy cloud of gas and dust surrounding the comet's nucleus, is expanding at a rate unlike anything scientists have observed before. Comas are a standard feature of comets, but the coma of 3I/Atlas is outpacing all expectations, reaching an unprecedented size. The coma of 3I/Atlas has been measured at over 348,000 kilometers in diameter, more than 3 times the size of the Earth's orbit around the Sun. For context, the coma of most comets is typically much smaller, often no larger than the distance from the Earth to the Moon. To have a coma stretch across a distance larger than Mercury's orbit is unheard of in cometary science. This expansion is not just an issue of scale, it's a signal that something is different about the comet's composition. Unlike most comets, which are dominated by water ice, 3I/Atlas has been found to have a carbon dioxide, CO2, rich coma. In most comets within our solar system, water vapor makes up the bulk of the outgassing material, with CO2 playing a secondary role. But in 3I/Atlas, carbon dioxide is the dominant volatile. This significant shift in composition is a clue to the comet's origins and the conditions under which it formed. The presence of such a large CO2 component suggests that 3I/Atlas did not form under the same conditions as typical comets. Most comets in our solar system formed in the colder outer regions, where CO2 is able to freeze into solid ice. However, 3I/Atlas likely formed around another star in a region where the temperature conditions were different, perhaps cooler or with a different mix of materials. This means that 3I/Atlas's outgassing is much more volatile than that of most comets we're familiar with. CO2 sublimes at a lower temperature than water ice, which could explain the rapid brightening and massive coma expansion observed in recent months. But the growing coma and anti-tail are not the only peculiarities that are leaving scientists at a loss. The behavior of 3I/Atlas is sparking an ongoing scientific debate about the fundamental nature of comets. Some argue that this comet is merely an extreme example of typical cometary behavior, albeit one that exists outside the bounds of the models that we have used to describe such objects. Others suggest that the comet is so unusual that it might represent an entirely new class of object, something we've never encountered before in our solar system. The question remains, what is 3I/Atlas truly telling us? Is it just a more extreme version of a regular comet, or is it a reminder that the universe has phenomena that we can only begin to understand? The fact that its behavior so dramatically challenges established comet physics points to the possibility that we are observing a completely different kind of object, one that doesn't fit neatly into the categories we've developed to study comets. In the middle of September 2025, something extraordinary happened that sent shockwaves through the astronomical community. 3I/Atlas, already behaving in ways that defied expectations, began to glow with an eerie green light. This wasn't a subtle shift in color, this was a vivid, almost unnatural hue that painted the comet in a ghostly glow against the backdrop of space. The phenomenon was striking, and for scientists, it was a puzzle they had never encountered before. The green glow of a comet is not entirely unprecedented. In our solar system, we've seen comets display subtle green tints in their comas, usually associated with the presence of certain carbon-based molecules. But this wasn't just a fleeting glow, it was a stark, persistent illumination that seemed to demand an explanation. What was causing this strange green light, and why had it appeared now, at this particular stage in 3I/Atlas's journey? The answer lies in a molecule called C2, or diatomic carbon, which is notorious for producing a green emission when it absorbs ultraviolet, UV, light from the sun. In the specific wavelengths of UV light that are emitted by our star, the C2 molecules become energized, with their electrons jumping to higher energy states. As the molecules return to their lower energy states, they release energy in the form of light, at a wavelength of 516 nanometers, which is in the green part of the spectrum. This process, known as fluorescence, is the source of the green glow that has made 3I/Atlas so visually distinctive. But here's where the mystery deepens. Initial spectroscopic observations of 3I/Atlas suggested that the comet didn't contain the typical carbon compounds associated with this kind of fluorescence. Instead, the chemical analysis showed an abundance of carbon dioxide, CO2, and water vapor, with only trace amounts of the carbon-based molecules like C2 that would normally be responsible for such a glow. So, where was the C2 coming from, and why was it appearing in such an intense form? This apparent contradiction between the observed green glow and the chemical composition puzzled astronomers. If the comet didn't have the usual carbon compounds required for the green fluorescence, how was it producing this vivid light? The explanation may lie in the comet's outgassing behavior. As 3I/Atlas approached the Sun, the increase in solar radiation could have triggered the sublimation of previously inaccessible materials within the comet's nucleus. These materials, which may have been locked in deeper layers of the comet's icy interior during its long journey through interstellar space, could be releasing carbon-bearing compounds for the first time. It's possible that the carbon dioxide in the comet's coma is undergoing photodissociation, a process in which solar radiation breaks down the CO2 molecules into simpler carbon compounds, including carbon monoxide, CO, and atomic carbon. Once released, these newly formed carbon atoms could bond together to create diatomic carbon, C2, which then emits the green glow when it absorbs UV light. This would explain why the comet, despite initially appearing to lack the necessary compounds, began to glow with this vivid, green hue. It's as if the comet's ancient chemistry, untouched for millions of years, was suddenly coming to life in a burst of energy as it neared the sun. But the implications of this discovery extend far beyond just understanding the green glow. The presence of C2 and other carbon-based molecules in the comet's coma raises profound questions about the chemical composition of interstellar objects. 3I/Atlas, formed around a star light-years away from our own, could contain chemical signatures that are not only foreign to our solar system but potentially offer a glimpse into how alien chemistry works in other star systems. The carbon molecules released from 3I/Atlas may have formed under conditions that are vastly different from those that shaped the chemical makeup of our solar system. What if this comet contains molecular structures that have never been seen before, or compounds that behave in ways entirely alien to our understanding? Could this be the first evidence of extraterrestrial chemistry, molecules that don't fit within the models we've built based on our solar system's chemistry? If 3I/Atlas is releasing carbon molecules that were never exposed to the same radiation or environmental conditions as the materials in our solar system, it could be giving us a first look at the chemical diversity that exists across the galaxy. The potential discovery of alien chemistry within this interstellar traveler could be groundbreaking for fields like astrobiology and planetary science, raising the possibility that the building blocks of life, or even life itself, might form under conditions far different than those found on Earth. The green glow of 3I/Atlas is more than just a strange visual phenomenon. It is a window into the alien origins of this comet, offering insights into the complex chemical processes that take place in distant star systems. And as we continue to observe the comet's behavior, the mystery of its glowing tail may unravel even further, revealing more about the extraordinary chemistry that exists in the far reaches of the universe. The question now is, what else could 3I/Atlas be hiding within its icy, carbon-rich depths? As 3I/Atlas approaches the most critical phase of its journey toward perihelion, astronomers face a daunting challenge. The observational window is rapidly closing. The comet is set to undergo its most dramatic transformations as it nears the sun, yet Earth-based telescopes are running out of time to capture the data needed to understand what's truly happening. The reason for this is simple, yet frustrating: solar glare. When a comet nears the sun, the increasing intensity of sunlight makes it more and more difficult to observe. The comet's brightening, expected outgassing, and tail development should all be most noticeable around perihelion, but during this period, the comet will be positioned so close to the sun and the sky that its faint light will be drowned out by the overwhelming glare. Simply put, Earth-based telescopes will no longer be able to track the comet as it passes the most critical point in its journey. The term for this astronomical phenomenon is superior conjunction, a period when a celestial object, in this case, 3I/Atlas, moves too close to the sun and the sky for observations to be made from Earth. As 3I/Atlas reaches this phase, astronomers will have no choice but to rely on alternative observation platforms to continue monitoring its behavior. The implications are profound. In theory, perihelion is when 3I/Atlas should be at its most active. As the comet is bombarded by the sun's intense radiation, its outgassing will likely reach its peak, potentially triggering massive bursts of dust and gas. This is the moment when the comet may reveal its true nature, whether it will explode with activity or undergo some other transformation we've never witnessed. But with Earth-based telescopes effectively blind during this time, the most important observations will be lost to us unless other systems can step in to fill the void. Enter space-based observatories and Mars orbiters. While Earth-based telescopes struggle to peer through the glare, space telescopes like the James Webb Space Telescope, JWST, and the Hubble Space Telescope are positioned far enough from the sun to offer a clearer view. These observatories, however, are not without their limitations. JWST, for instance, can observe objects in the infrared spectrum, and while this is helpful for tracking thermal emissions, its ability to gather detailed optical images of 3I/Atlas is reduced when the comet is so close to the sun. Still, these space-based instruments will provide invaluable insight, capturing spectroscopic data that will allow scientists to continue tracking the comet's chemical composition, temperature, and overall activity. But perhaps the most important observers during this critical period will be the Mars orbiters. Mars, sitting at a comfortable distance from the Sun, will provide a vantage point that Earth simply cannot. Several spacecraft orbiting Mars will be positioned perfectly to observe the comet as it moves toward perihelion, during a time when Earth will be completely unable to do so. These orbiters, including Mars Express, MAVEN, and Mars Reconnaissance Orbiter, MRO, will serve as humanity's eyes in the solar system. The spacecraft currently orbiting Mars have been designed to study the red planet's atmosphere and surface, but their instruments are more than capable of observing distant objects like 3I/Atlas. Equipped with high-resolution cameras, spectrometers, and specialized instruments, these spacecraft will have the unique ability to capture images and data about the comet's coma, tail, and nucleus at a time when Earth is effectively blind. This will be an unprecedented opportunity for Mars-based observations to take center stage, and scientists are keenly aware of the responsibility placed on these spacecraft to gather as much data as possible. The MAVEN spacecraft, for example, is equipped with instruments designed to analyze the atmosphere of Mars but is also capable of studying the ionized gas surrounding 3I/Atlas, especially as it interacts with the solar wind. The Mars Reconnaissance Orbiter boasts an imaging system with unparalleled resolution, capable of capturing structural details of the comet's coma and tail. Even though these instruments are optimized for Mars-related observations, they will become essential tools in tracking 3I/Atlas during its most volatile period. For the scientists involved, the urgency is palpable. This is a race against time. As the comet nears its closest approach to the Sun, every moment becomes crucial. With perihelion fast approaching, the window to study 3I/Atlas before it disappears into solar glare is shrinking. The data gathered in the coming weeks could answer questions that have haunted astronomers for years. What is the true composition of this interstellar visitor? How does it behave as it encounters the Sun's heat for the first time? And what mysteries lie hidden within its coma and tail, waiting to be revealed? As the comet disappears behind the Sun, the observations made by Mars orbiters and space-based telescopes will be our only window into the unfolding drama. The data collected during this brief, critical period may provide answers that could reshape our understanding of comets, interstellar objects, and the processes that govern the evolution of cosmic bodies. But the clock is ticking, and time is running out. As 3I/Atlas continues to defy all expectations, the growing alarm within the scientific community is palpable. What was initially dismissed as an oddity in the solar system has transformed into something far more mysterious, even unsettling. Astronomers are grappling with the reality that they are witnessing something unprecedented, an interstellar object that is rewriting the rules of cometary science. With each new observation, the comet seems to shatter yet another long-held assumption about how comets behave. The comet's unusual trajectory, rapid brightening, eerie green glow, and anti-tail have pushed astronomers to the limits of their understanding. Comets are supposed to behave in a predictable way as they pass near the Sun, undergoing gradual brightening as solar radiation sublimates their icy cores. Yet, 3I/Atlas has thrown all of these models into disarray. Its unexplained brightening, far outpacing anything predicted, suggests that we might not be dealing with a simple, run-of-the-mill comet. Instead, we could be witnessing an object whose internal processes are as foreign to us as the stars from which it originated. As the data continues to pour in, the excitement among scientists is tempered by an increasing sense of uncertainty. For every breakthrough in understanding, new questions emerge. Why is the comet's tail pointing toward the Sun, something that should be impossible by our current understanding of cometary physics? What is the source of its green glow, and why does it seem to be defying the basic principles of chemistry? These are not questions that can be answered by existing models, which were built based on the behavior of comets formed within our solar system. 3I/Atlas is something altogether alien, and its unexpected behaviors are pushing researchers to rethink their entire approach to studying these objects. The excitement is undeniable, but it is tempered by the fear of the unknown. Could 3I/Atlas be the first in a new class of objects that behave fundamentally differently from any known comet? Dr. Matthew Knight, a comet researcher at the University of Maryland, commented on the rapid brightening observed in the comet in September 2025, noting, "This is unlike anything we've seen before." The sudden acceleration in brightness suggests processes that we don't fully understand. This comet might not be a comet at all, at least not in the traditional sense. This uncertainty is mirrored by other astronomers who express both fascination and trepidation as they watch 3I/Atlas defy the laws of cosmic behavior that have stood for centuries. The scientific community's reaction has been a mixture of awe, disbelief, and urgency. While the comet's strange behaviors are undoubtedly exciting, offering a glimpse into a corner of the universe we have never explored before, they also raise uncomfortable questions. Are we witnessing the discovery of a new type of celestial object, one that operates under a completely different set of physical and chemical rules? Or are we simply encountering an anomaly that will, eventually, be understood through the lens of traditional comet science, albeit with some unexpected twists? Dr. Carl Sagan, had he been alive to witness this, might have remarked on how moments like these, when the universe throws something completely new and unpredictable our way, are the very essence of scientific exploration. But even Sagan would have likely been taken aback by the speed at which 3I/Atlas is evolving. Some astronomers are beginning to suspect that this comet's transformation might be indicative of something even more radical than they initially thought. Could the processes at play here, volatiles sublimating, carbon compounds fluorescing, point to chemistry and physics that are far more diverse than we imagined? The excitement is not only driven by the promise of new knowledge but also by the sheer mystery of it all. The comet's strange behavior is pushing the boundaries of what we know about the cosmos, testing our most fundamental assumptions. The fact that 3I/Atlas is likely a relic from another star system only intensifies the intrigue. If the comet behaves in ways that no object in our solar system could ever replicate, what does that say about the wider universe? Are there other regions of space where conditions exist that create objects like 3I/Atlas, comets that behave radically differently from the ones we've come to know? The growing concern within the scientific community is not just about the comet's strange behaviors, but about the implications these behaviors have for our understanding of comets, interstellar bodies, and even the potential for extraterrestrial life. As astronomers work to piece together a coherent theory, one thing becomes abundantly clear: 3I/Atlas is more than just a comet. It is a mystery wrapped in an enigma, and it's making every researcher question the very foundations of comet science. In a rare moment of candor, Dr. Amy Mainzer, a planetary scientist at NASA's Jet Propulsion Laboratory, remarked, "We're facing a challenge. This comet may be revealing something we never expected, a deeper understanding of our universe that may force us to revisit the very laws of physics we thought were unshakable." Her words capture the essence of the scientific community's reaction, a mixture of excitement, disbelief, and the growing realization that we are on the verge of discovering something extraordinary. As 3I/Atlas approaches its closest point to the Sun, the excitement surrounding the comet's mystery only grows. The days leading up to perihelion are crucial. Scientists are fully aware that they may have only a limited amount of time to observe this enigmatic object before it disappears behind the sun's glare. The growing alarm is not just about its behavior, but about what that behavior means for our place in the universe. Could this comet be offering a glimpse into a new chapter of cosmic discovery? Only time, and careful observation, will tell. As 3I/Atlas approaches its closest point to the Sun, one critical moment in its journey offers humanity an unprecedented opportunity to observe this interstellar visitor with unprecedented detail, its flyby of Mars. On October 3, 2025, 3I/Atlas will pass within 30 million kilometers of the red planet, a relatively close approach by cosmic standards. While Earth-based telescopes will struggle with the increasing solar glare, the Mars orbiters will be perfectly positioned to capture the data that could help unravel the comet's mysteries. Mars, sitting at a relatively safe distance from the Sun compared to Earth, provides an ideal vantage point for spacecraft that are already in orbit around the planet. These orbiters, such as the Mars Express, MAVEN, and the Mars Reconnaissance Orbiter, MRO, will have the rare chance to monitor 3I/Atlas as it nears its closest approach to the Sun, giving scientists crucial insights into the comet's behavior as it undergoes intense solar heating. While these spacecraft were originally designed to study Mars and its atmosphere, their sophisticated instruments are more than capable of turning their gaze on the comet, offering some of the best opportunities for data collection. Mars Express, launched by the European Space Agency, has already been instrumental in mapping the Martian surface and studying the planet's atmosphere. Equipped with high-resolution imaging and spectrometric tools, Mars Express will be able to capture detailed images of 3I/Atlas's coma and tail as it speeds past. The spacecraft's visual monitoring camera, VMC, and high-resolution stereo camera, HRSC, could provide some of the clearest photographs of the comet's nucleus, as well as insights into its composition and activity. The close approach to Mars gives this orbiter a unique opportunity to study the comet's interaction with the solar wind, helping scientists understand the dynamics of its outgassing and tail development. MAVEN, Mars Atmosphere and Volatile Evolution Mission, another crucial player, is tasked with studying the Martian atmosphere. However, its suite of instruments, designed to analyze the interaction between solar radiation and atmospheric gases, could be repurposed to monitor 3I/Atlas's coma and how the solar wind interacts with the comet's ionized gas. MAVEN's ion and neutral mass spectrometer could reveal the chemical composition of the comet's coma, providing essential information about the volatile ices that are being released as the comet moves closer to the Sun. These readings could also help researchers investigate the potential for chemical processes that are unique to interstellar objects. The Mars Reconnaissance Orbiter, MRO, perhaps the most well-equipped spacecraft for this task, is outfitted with the HiRISE, High-Resolution Imaging Science Experiment, camera, which boasts the ability to capture images with an unprecedented level of detail, resolving surface features smaller than 30 centimeters across from its orbital altitude. Even though 3I/Atlas will pass far from Mars, the exceptional resolution of HiRISE might still provide critical details of the comet's nucleus and its developing coma, offering insights into the composition and structure of this interstellar traveler. MRO's instruments will also be able to detect the presence of key volatile compounds, providing invaluable data that would be difficult to obtain from Earth-based observations. But despite the remarkable capabilities of these spacecraft, observing an object like 3I/Atlas poses significant challenges. The comet is moving at a tremendous speed, far faster than anything in our solar system. At roughly 130,000 miles per hour, 58 kilometers per second, its rapid motion across the sky requires spacecraft to make adjustments to their observation plans. These spacecraft were not designed with such fast-moving interstellar objects in mind, and tracking them with the required precision presents a technical hurdle. Instruments that were initially designed for planetary studies must now be recalibrated to study a fleeting visitor that will be gone in the blink of an eye. Moreover, 3I/Atlas's unpredictable behavior means that scientists can't rely on predetermined observation schedules. The comet's unexpected brightening, rapid changes in its tail, and other bizarre behaviors make it difficult to know exactly when the most significant phenomena will occur. This uncertainty means that the Mars orbiters must be ready to adjust on the fly, taking advantage of any opportunity to observe the comet in the few days leading up to its closest approach. However, if these spacecraft can successfully track 3I/Atlas, the scientific breakthrough could be monumental. The data they collect will provide critical insights into the behavior of interstellar objects and the unique processes at play when such objects interact with the Sun's radiation. This flyby could offer a glimpse into the dynamics of comets from other star systems, shedding light on the chemical and physical properties that set them apart from comets native to our solar system. For astronomers, the Mars flyby represents a golden opportunity to study 3I/Atlas in greater detail than ever before. It's a rare event, one that might not come again in our lifetimes, and scientists are eager to capture every bit of data they can. The knowledge gained during this brief window of observation could pave the way for a new understanding of how interstellar objects behave and what secrets they may hold about the universe beyond our own star. As 3I/Atlas nears perihelion, the timing of its closest approach to the Sun coincides with a difficult reality for astronomers: superior conjunction. This period, which occurs when the comet is positioned too close to the Sun in our sky, will effectively render 3I/Atlas invisible to Earth-based telescopes. The Sun's overwhelming glare will obscure any light from the comet, making observation nearly impossible. The comet's most critical period of activity, when solar heating should trigger the most dramatic changes, will take place largely hidden from view. The superior conjunction will mark the beginning of an observational gap, a critical phase when researchers will have to rely on data from spacecraft positioned further from the Sun, namely Mars orbiters and space-based observatories like the James Webb Space Telescope and Hubble. While these instruments are capable of observing the comet at certain wavelengths, they are far from ideal for studying the full range of outgassing and structural changes occurring in the coma and tail. As the comet fades from view, there is a growing sense of scientific loss. Theories about 3I/Atlas's behavior, such as whether it will experience massive outbursts, fragmentation, or shifts in its chemical composition, may go unanswered for weeks. This window of invisibility means that some of the comet's most transformative changes could occur out of sight, leaving astronomers to speculate and model its behavior based on the limited data already collected. With the comet hidden by solar glare, Earth-based telescopes will have no ability to capture the comet's critical moments. The lost opportunity for direct observation during superior conjunction is a source of concern. For astronomers, this represents a rare and unfortunate gap in data collection, one that could hinder the full understanding of 3I/Atlas's transformation. The timing of this period makes it particularly frustrating. This is when 3I/Atlas will be at its most active, yet the best instruments available will be unable to record what might be some of the most remarkable moments in the comet's life. The absence of direct observation for a month or more only intensifies the need for accurate data collected beforehand. Scientists are now facing the delicate task of interpreting the comet's behavior during the few days it will be visible before disappearing into the Sun's glare. And as 3I/Atlas vanishes, questions mount: what will it look like when it reappears? How will it have changed under the influence of the Sun's radiation? Will we ever fully understand what happened during its time in the unseen zone, or will those answers remain locked away until it's too late? As 3I/Atlas speeds toward its closest approach to the Sun, its perihelion, the comet stands on the precipice of a dramatic transformation. The period surrounding perihelion, occurring around October 29th to 30th, 2025, marks a crucial moment in the comet's journey. This is the point where solar radiation will bombard the comet with the most intense heat it has ever experienced, causing it to undergo extreme changes. For astronomers, this event holds the potential for scientific revelations that could radically reshape our understanding of comets, particularly those from beyond our solar system. At perihelion, 3I/Atlas will be located at just 1.36 to 1.4 astronomical units, AU, from the Sun, just slightly closer than Mars's average distance from the Sun. At this critical distance, the Sun's intense radiation will trigger the sublimation of volatile materials in the comet's nucleus, particularly carbon dioxide, CO2, and water ice. These materials will transition from solid to gas, forming the coma and tail that characterize a comet. However, the amount of energy involved is enormous. The increase in temperature could lead to dramatic outgassing events, potentially altering the structure of the comet in ways we have never observed before. What makes this perihelion passage particularly significant is that 3I/Atlas is no ordinary comet. It is an interstellar visitor, a relic from another star system, and as such, its behavior could differ radically from comets native to our solar system. The volatile ices within the comet's nucleus, which have never before been exposed to the Sun's radiation, could sublimate in unpredictable ways. The explosive outgassing we expect to see at perihelion could reveal hidden details about the comet's internal composition, offering a glimpse into its ancient, interstellar chemistry. Yet, these transformations carry inherent risks, not just for our understanding, but for the comet's survival. Fragmentation is one of the most pressing concerns for astronomers. Comets are fragile bodies, often held together by weak forces between ice and dust particles. The intense solar radiation at perihelion will cause the comet to heat up rapidly, creating a buildup of internal pressure as volatile materials vaporize. If the forces involved are too great, they could cause the nucleus to break apart, potentially creating a debris cloud or smaller fragments. This phenomenon has been observed before with other comets, such as Comet Shoemaker-Levy 9, which fragmented under the tidal forces of Jupiter in 1992. The fragmentation of 3I/Atlas could create a spectacular display of dust and gas, but it would also make it harder for astronomers to study the comet as a whole. Instead of a single nucleus, we might be left with a scattered debris field, further complicating efforts to understand its origins and composition. But fragmentation is not the only risk. The comet's structure itself could be altered in ways that we cannot predict. 3I/Atlas's large CO2-dominated coma, already far larger than any comet we've observed before, suggests that the nucleus might be loosely bound, and that thermal stresses could cause significant shifts in its shape or surface properties. Thermal expansion, the rapid heating and cooling of the comet's surface as it orbits the Sun, could lead to cracks, landslides, or even the disintegration of sections of the nucleus. This might explain some of the comet's erratic behavior in the lead-up to perihelion, including its rapid brightening and the shifting characteristics of its tail. As 3I/Atlas nears the Sun, the internal dynamics of the comet will become increasingly unstable, and its physical integrity will be put to the test. Despite these risks, the perihelion encounter also offers an unparalleled scientific opportunity. The explosive activity expected from 3I/Atlas as it nears the Sun could provide insights into the composition of interstellar objects, as well as the processes that drive the evolution of comets. By studying the outgassing and any potential fragmentation events, astronomers hope to gain clues about the chemical compounds present within the comet, particularly those that may be unique to interstellar objects. What is truly fascinating about 3I/Atlas is that it carries with it the chemical signatures of a star system that we have never seen. The CO2-dominated coma already points to differences in formation conditions compared to solar system comets. Unlike comets that formed in the cold, distant regions of our solar system, 3I/Atlas likely originated in a region around another star where the conditions allowed CO2 to freeze out before water did. Understanding how the comet behaves under solar heating may provide us with new models for how such interstellar objects evolve as they encounter a star. Furthermore, the outgassing process itself is a critical area of study. It's not just about the composition of the gas, it's also about how the gas and dust interact with solar radiation. How quickly do they escape from the nucleus? What kind of dust grains are involved? By examining the way 3I/Atlas sheds material, scientists can learn more about the basic physical processes that drive cometary behavior and how these processes might differ in other star systems. 3I/Atlas's perihelion pass offers a window into new astrophysical realms, providing insight into objects that have traveled through space for millions of years before finally entering our solar system. It is not just a comet, it is a relic of a different time and place in the universe, one that might help us understand more about the formation and evolution of star systems across the galaxy. If we can capture the data during this critical time, it could be the breakthrough scientists have been hoping for, a moment that transforms our understanding of the cosmos. The questions surrounding 3I/Atlas are far from answered, but perihelion will be the time when the comet either reveals its secrets or fades into the void. The science of this moment, as it faces its greatest encounter with the Sun, holds the potential to reshape everything we thought we knew about comets and interstellar bodies. The arrival of 3I/Atlas in our solar system is not an isolated event. It is part of a rare and awe-inspiring pattern, interstellar objects passing through our cosmic neighborhood from distant stars. Before 3I/Atlas, two other interstellar visitors, Oumuamua and Borisov, had already made their mark in the astronomical community, challenging our understanding of space in ways we hadn't expected. By comparing these objects to 3I/Atlas, we can better appreciate what makes this comet so unique and why its behavior is forcing scientists to rethink the nature of interstellar bodies. When Oumuamua was first spotted in 2017, its elongated shape and erratic movement immediately raised questions. It was unlike any asteroid or comet that had been observed before. For one thing, it exhibited an unexpected non-gravitational acceleration, a speed increase that couldn't be explained by the sun's gravitational pull alone. This led some to propose outgassing as a possible cause, even though there was no visible tail or coma like that of a traditional comet. Others suggested that Oumuamua could be an artificial object, though this theory remained speculative. What was clear, however, was that this object was unlike anything our models predicted. It didn't fit neatly into the categories we had developed for comets and asteroids. Instead, Oumuamua forced us to consider the possibility that interstellar objects could have completely different properties than the ones we are accustomed to in our solar system. 2 years later, in 2019, the second confirmed interstellar object, Comet Borisov, passed through our solar system. In stark contrast to Oumuamua, Borisov was more familiar in appearance, a typical comet, with a visible tail and coma. It exhibited classic cometary behavior as it passed near the sun. However, its chemical composition told a different story. Spectroscopic observations revealed that Borisov contained an unusual mix of carbon monoxide and other volatile materials, unlike those found in solar system comets. Its composition hinted at formation conditions that were radically different from those that shaped comets like Hale-Bopp or Halley. Borisov wasn't just another comet, it was a messenger from another star system, one whose chemistry diverged from our own solar system standard. And now, 3I/Atlas has arrived, another interstellar object, but one whose behavior has defied expectations even more dramatically than its predecessors. Unlike Oumuamua, which presented an enigmatic shape and movement, 3I/Atlas behaves like a traditional comet in many ways, forming a coma, exhibiting a tail, and brightening as it nears the sun. Yet its green glow, anti-tail, and rapid brightening challenge everything we know about comets. The presence of carbon dioxide, CO2, as the dominant volatile in its coma, rather than water vapor, points to a different formation environment. The size and composition of its coma, too, are unprecedented, expanding to dimensions much larger than expected. This raises a key question: is 3I/Atlas just an extreme version of a regular comet, or is it telling us something fundamentally new about the nature of interstellar objects? What makes 3I/Atlas stand apart from both Oumuamua and Borisov is the combination of features that no previous object has exhibited. It has characteristics of both cometary behavior and unique interstellar composition, merging the lines between what we traditionally classify as comets, asteroids, and unknown interstellar bodies. The green glow and the anti-tail are phenomena that have never been observed in interstellar visitors before, adding another layer of mystery to its already strange behavior. The outgassing, dominated by CO2, has raised speculation about whether this comet formed in a region of space where the chemical conditions were vastly different from our solar system. The lessons learned from Oumuamua and Borisov are crucial for understanding the diversity of interstellar objects and their behavior. With Oumuamua, we learned that objects from other star systems might not conform to our established models at all. It hinted at the possibility that interstellar objects could have unique properties, either due to their formation in different star systems or because they have been exposed to conditions that we don't typically encounter in our solar system. Borisov showed us that even comets from other star systems could behave in unexpected ways, with different chemical compositions that hint at distinct formation environments. The combination of these two discoveries told us that interstellar objects come in a wide range of forms and behaviors, far beyond the types of bodies we find in our own solar system. In the case of 3I/Atlas, we are now learning that these interstellar visitors don't follow predictable patterns. Each one has offered a new wrinkle, forcing astronomers to expand their theories about how small bodies evolve and behave as they travel across interstellar space. The chemical compositions, physical structures, and even behavioral patterns of interstellar objects appear to vary greatly depending on their origins. And 3I/Atlas is proving to be one of the most extreme examples yet. By studying 3I/Atlas, we can gain insight into the processes that govern the formation and evolution of comets across the galaxy, and possibly even across other galaxies. These objects offer us a window into the conditions that exist in other star systems, where temperatures, chemical compositions, and radiation environments may be radically different from our own. Each interstellar visitor, whether it's Oumuamua, Borisov, or 3I/Atlas, teaches us more about the vast diversity of the universe, where each new discovery expands our understanding of the cosmos. But the true significance of these objects lies in their ability to challenge the assumptions we have made about the universe. As each new interstellar object passes through our solar system, it forces us to reconsider our understanding of what is possible in space, making the study of these visitors crucial to unlocking the broader mysteries of the universe. As the strange behavior of 3I/Atlas unfolds, scientists are engaged in intense debates about what exactly they are witnessing. The comet's unprecedented characteristics, its eerie green glow, rapidly accelerating brightness, anti-tail, and expanding coma, have left researchers scrambling to build a coherent theory that can explain the object's behavior. But the deeper scientists dive into the data, the more contradictory findings emerge, making it increasingly difficult to reconcile the various observations. One of the most pressing challenges is the modeling of 3I/Atlas's behavior. Traditionally, comets follow certain predictable patterns based on their distance from the Sun and the types of volatile materials within their nuclei. Cometary models are well established, offering relatively straightforward predictions about how an object will behave as it heats up and begins to outgas. Yet, 3I/Atlas is defying these models at every turn. Its rapid brightening, far more intense than expected, has sent astronomers back to the drawing board. Could there be volatiles we haven't accounted for, or is the comet behaving in a fundamentally different way due to its interstellar origin? The composition of the comet adds another layer of complexity to the debate. As 3I/Atlas approaches the Sun, the amount of outgassing it is experiencing should be directly related to the composition of its nucleus, but the data is difficult to interpret. Initially, astronomers detected high concentrations of carbon dioxide, CO2, in the comet's coma, yet CO2 is not typically the dominant volatile in most comets. This discovery has led to questions about the formation conditions of the comet, and whether it is composed of materials that are vastly different from comets in our solar system. Furthermore, the presence of C2, diatomic carbon, and the comet's green glow have raised additional uncertainties. Where did these molecules come from, and why are they being released at such an alarming rate? If carbon dioxide is the main volatile, how is this leading to the fluorescence of C2? To complicate matters further, the structure of the comet's tail, pointing directly toward the Sun rather than away from it, has thrown cometary physics into disarray. How is it possible for a comet's tail to behave in such an unpredictable way? Traditional models of cometary tails rely on solar radiation pressure pushing material away from the Sun, yet 3I/Atlas seems to be violating this basic rule. Could there be a more complex set of forces at play, perhaps related to the comet's rotation, surface properties, or even its interactions with the solar wind? Some scientists have proposed that the anti-tail might be caused by large dust grains or plasma dynamics, yet no one is certain. All of these contradictions have left the scientific community grappling with uncertainty. The debate is not just about the specifics of 3I/Atlas, but about the very nature of cometary science itself. What are we really seeing here? Is 3I/Atlas a comet like any other, simply behaving in extreme ways due to some unique combination of factors? Or does its behavior signal the need for new theoretical frameworks that might apply not only to this comet but to other interstellar visitors as well? The struggle to piece together a coherent theory from contradictory data has become one of the defining features of the scientific inquiry into 3I/Atlas. Every new observation seems to raise as many questions as it answers. In the face of such uncertainty, some scientists are calling for more radical approaches to studying these interstellar objects. As 3I/Atlas continues its journey, it may be the catalyst for a paradigm shift in how we understand comets and other small bodies that travel across the galaxy. As astronomers wrestle with the bizarre behavior of 3I/Atlas, there remains the possibility that the comet's strange characteristics are the result of extreme but natural conditions, rather than exotic or unknown phenomena. While some theories suggest that the comet may be defying the laws of physics, it is important to consider that natural processes, albeit in extraordinary conditions, might still account for its behavior. One of the key factors in explaining the comet's unexpected behavior lies in its composition. 3I/Atlas's dominance of carbon dioxide, CO2, in its coma, rather than the usual water ice, suggests that it formed in a much colder, more distant region of its parent star system. In our solar system, CO2 freezes at a much lower temperature than water ice, and comets that originate in the outer solar system typically contain a greater proportion of water ice. If 3I/Atlas formed in a similar environment around its original star, the CO2-rich coma could explain its rapid sublimation as it approaches the Sun's CO2 sublimes at lower temperatures than water ice, which would account for the comet's accelerated outgassing and dramatic brightening. This behavior might not be unique to 3I/Atlas but could be a feature of objects from colder regions of other star systems. Another possible natural explanation involves plasma physics. The anti-tail, in particular, has sparked a number of hypotheses related to interactions between charged particles in the comet's coma and the solar wind. When the sun's radiation ionizes the gas surrounding a comet, a plasma tail is created. Normally, this plasma is pushed away from the sun by radiation pressure. However, if the comet's nucleus is ejecting large dust grains or if the comet's plasma dynamics differ from typical comets, these particles could maintain trajectories that appear to point toward the sun. Such plasma-induced behaviors have been observed in other cosmic phenomena, where electromagnetic forces and solar wind interactions create seemingly impossible structures in space. If this is what's happening in 3I/Atlas, it could be a matter of plasma dynamics at play, rather than anything fundamentally anomalous. The theory of a slow rotation could also offer an explanation for the comet's unusual behavior. If 3I/Atlas has a slow rotation rate, its surface could be experiencing extreme temperature differences between the day and night sides. This would concentrate the outgassing in specific areas of the nucleus, leading to highly localized bursts of material that could form the comet's unusual tail and coma structure. This is a natural effect of cometary behavior, albeit one that has not been fully explored in interstellar comets before. The slow rotation hypothesis would explain the uneven ejection of gas and dust from the comet's surface, potentially creating the appearance of a tail that does not conform to the usual cometary patterns. Finally, space-dust interactions could be contributing to the comet's rapid brightening. In the cold reaches of interstellar space, cosmic dust and radiation interact with the comet's surface in ways that we don't yet fully understand. The dust may be impacting 3I/Atlas in such a way that it causes faster sublimation of the volatile materials, further accelerating its brightening and outgassing. This could explain the comet's sudden acceleration in brightness without invoking exotic theories. While these natural explanations may not account for every detail of 3I/Atlas's behavior, they suggest that we might be witnessing the effects of extreme, yet plausible, natural processes. The unusual composition, plasma interactions, slow rotation, and dust dynamics might all be playing a role in creating the comet's unique characteristics, offering a more mundane, albeit fascinating, interpretation of its behavior. As the mystery of 3I/Atlas deepens, a wave of speculative and fringe theories has emerged. While the comet's unusual behavior has prompted some natural explanations, others are considering the more extraordinary possibility that we may be witnessing something beyond the scope of traditional science. These theories push the boundaries of what we know and venture into the realm of the speculative, offering imaginative solutions to the comet's enigmatic features. One of the most persistent fringe theories involves the idea that 3I/Atlas could be an artificial object, perhaps a probe or some form of technology sent from another civilization. This theory gained traction after the unusual behavior of Oumuamua in 2017, with its unexpected acceleration and elongated shape sparking debates about its potential artificial origins. The idea is that the anti-tail, rapid brightening, and green glow might not be the result of natural processes but could indicate directed energy emissions or sensor activation. In this scenario, 3I/Atlas could be an ancient probe, a long-dormant artifact awakening as it nears our sun, ready to send data back to its creators. While there is no direct evidence to support this theory, it continues to capture the imagination of some researchers, pushing the boundaries of scientific thought. Another theory that has captured the attention of fringe thinkers is the living plasma hypothesis. In this speculative scenario, 3I/Atlas could be a plasma-based organism of sorts, formed from charged particles and dust in deep space. Similar to how complex plasma formations can exhibit properties of living organisms under certain conditions, 3I/Atlas might be exhibiting behaviors that mimic biological processes. This would mean that the comet's unusual outgassing, its glowing green color, and even its rapid brightening could be signs of an organism-like process unfolding. While the science behind this idea is purely theoretical, it presents a radical reinterpretation of what it means to be alive in the universe, challenging conventional biology. The exotic matter theory takes another leap into the unknown, suggesting that 3I/Atlas could be composed of materials or operate according to physical principles that we have yet to discover. In this scenario, the comet's behavior is the result of unknown forms of dark matter or other exotic particles that interact with solar radiation in ways we cannot yet comprehend. The rapid acceleration, strange tail, and green glow could all be the result of gravitational anomalies or energy release mechanisms not observed in known matter. This theory challenges our fundamental understanding of physics itself, suggesting that the comet might be composed of materials that obey different rules than the matter we encounter every day. While these theories remain on the fringes of scientific thought, they highlight the extraordinary nature of 3I/Atlas. In many ways, the comet forces us to stretch the boundaries of scientific imagination, asking us to consider possibilities that, at first glance, seem outlandish. And perhaps, that is the true mystery of 3I/Atlas. It presents a cosmic puzzle that challenges everything we think we know about space, time, and the laws of nature. As 3I/Atlas races toward its final encounter with the sun, the scientific community is holding its breath. This is the moment when we might finally unlock the mysteries surrounding this interstellar traveler. The comet's approach to perihelion represents not just a dramatic conclusion to its cosmic journey, but a profound opportunity to advance our understanding of the universe. For scientists, the stakes have never been higher. What will we learn from this enigmatic object, and how will it change the way we view the cosmos? In the days leading up to perihelion, astronomers are hoping to gain insights into the formation and evolution of comets, not just those in our solar system, but those from other star systems. 3I/Atlas provides a rare opportunity to study the chemical and physical properties of a comet that has traveled across the galaxy, carrying with it clues about the conditions around its parent star and the processes that shaped its formation. With every new discovery about 3I/Atlas's behavior, scientists are piecing together a more complete picture of how comets, and possibly even planetary systems, form in different regions of the universe. One of the most important things astronomers hope to learn from 3I/Atlas's encounter with the sun is how interstellar objects interact with solar radiation. Unlike comets that have evolved in our solar system, 3I/Atlas has never been exposed to the intense heat of a star like the Sun. How will its volatile materials behave under solar radiation, and what can that tell us about the chemistry and composition of other star systems? In the coming days, as the comet's coma expands and its tail shifts, scientists will study how the comet responds to the Sun's energy. Will it fragment, as some predict, or will it remain intact, revealing a wealth of interstellar chemistry? The data gathered will deepen our understanding of exotic materials and the conditions under which they form, opening new avenues for studying the diversity of the universe. Beyond the scientific implications, 3I/Atlas's visit to our solar system holds broader significance for planetary defense. The unexpected arrival of this interstellar object has shown us how ill-prepared we are to track and study objects from outside our solar system. While 3I/Atlas poses no danger to Earth, its close approach highlights the need for better tools and systems to monitor interstellar visitors. As more and more interstellar objects are discovered, many of which may pass through our solar system undetected, we must rethink our approach to planetary defense. 3I/Atlas could serve as a case study for developing better detection methods, enabling us to identify future interstellar objects early enough to understand their potential threat or opportunity before they reach Earth. Perhaps the most profound implication of 3I/Atlas's journey is the way it challenges our perception of the cosmos. For centuries, we have looked up at the night sky and imagined the vastness of space, but our understanding of the universe has always been limited by the boundaries of our own solar system. 3I/Atlas, a visitor from another star system, has shattered those boundaries, forcing us to confront the reality that the universe is not just made up of stars, planets, and moons we know, but an entire multiverse of possibilities waiting to be explored. It is a reminder that there is so much more to learn, that we are only just beginning to scratch the surface of the vast cosmic tapestry that stretches across the galaxy and beyond. In the end, 3I/Atlas is more than just a comet. It is a cosmic riddle, a puzzle that has forced us to rethink everything we know about comets, interstellar bodies, and the processes that govern the universe. The final mystery remains: what will we truly learn about 3I/Atlas, and how will it reshape our understanding of the cosmos? Will it provide new insights into the nature of the universe, or will it raise more questions than answers? As it draws closer to the Sun, we are about to find out. Whether this comet ultimately reveals new layers of interstellar chemistry or confounds our expectations, one thing is certain: 3I/Atlas has already begun to change the way we view space, time, and the potential for life and science across the stars. The countdown to perihelion has begun, and in the coming days, 3I/Atlas will reveal its secrets. The implications for science, planetary defense, and our understanding of the universe are profound, and the answers it provides, or the mysteries it leaves behind, will echo in the annals of astronomical discovery for generations to come.